Greetings and welcome back to Chapter 12, Part 2. I sort of have a bone to pick with the way that the beginning of Chapter 12.3 is worded. And while I am one of the contributing authors to this book, which you can see in the front, I have tried to get them to reword this several times and they just kind of refuse. So let me just read very briefly. We're used to thinking about all materials being equal. This is what it actually says, okay? If a room is packed as tightly as possible with cats, we'd be surprised if people could move freely through it. But electrons and atomic nuclei may overlap to occupy the same physical space, unlike people and cats. Okay. First of all, that's garbage and nonsense. If you've ever tried, has anyone ever tried like picking up a cat? You cannot pack a room packed as tightly as possible with cats. I mean, what are you going to do? Try to stack them floor to ceiling in an elevator? A better analogy would be, trying to pack them tightly shoulder to shoulder. But then, even then, you could still step into an elevator that's filled with cats. Cats are, while yes, they're the same matter, right? They're the same kind of carbon or whatever that we're made out of. They can fit into places that we can't. Have you ever, like picked up a cat and stuffed it into the hood of your hoodie or something like that, right? They fit. Cats can fit in places that we can't. However, electrons and protons, or atomic nuclei, cannot fit in the same space. That's garbage. If an electron and a proton, or an electron and a neutron, hit the same point in space and time, you're going to end up with some kind of beta decay event or something like that. That's not what happens in stable atoms, okay? That's not how particle physics works. So regardless of what this says, that's not how things work. Electrons and protons cannot occupy the same physical space. They are both matter, okay? Unlike people and cats, who are still both matter. I really don't know what they were trying to go for here, but it's not very scientifically accurate. Whatever you do, don't try to stack a bunch of cats ceiling to floor. I mean, unless you want to get your face scratched off. Okay, enough fun with our book, huh? Let us remind ourselves of where we ended last time. We were talking about the red giant and how we ended up with a red giant. We had a main sequence star, like our sun, and eventually the core became more massive and smaller and more pressurized and hotter because the degenerate matter in the core of the star, the helium ash that built up, compressed down to become degenerate. That caused more matter to flow in from elsewhere in the star, and that caused more hydrogen burning out in the hydrogen shell around the core, and that caused a runaway energy generation effect that caused the star to blow up into becoming a red giant, right? At some point, eventually, the helium atoms began to fuse together in a process. I think actually, I forgot to mention that. When you bang two heliums together to make a beryllium, and then a third one joins the party to make a stable carbon atom, that's called the triple alpha process. An alpha particle is a helium nucleus. It's two protons, two neutrons. And so we call it the triple alpha process because we take three heliums, right, and smash them together to make a stable carbon, carbon 12, like the stuff that we're made out of. We talked a little bit about the helium flash. Oh, look, it's a lucky meal. We talked a little bit about the helium flash, and that, of course, is when the core of a star ignites its helium and it just goes up like a flash. Like the entire amount of degenerate helium in the core of a star like our sun will go up in a matter of minutes. That's why I call it the helium flash. And over the course of just a few hours, the entire core just kind of catches on fire, essentially, and releases uh, tons and tons of energy. Uh, Even all of the helium that's not degenerate down in the core is going to start fusing into carbon. And that's going to cause energy generation in the core of this star, the likes of which it has never seen. And that's going to cause, and it's tempting to think that the star is going to blow up or something like that, but what happens is the degenerate matter, that little, I drew it as a little blue dot, right? That degenerate helium is going to blow up and become non-degenerate. And so now we've got just regular helium, and it's burning into carbon, but we still also have hydrogen burning into helium. And so now we've got hydrogen burning into helium and helium burning into carbon, right? And with this tremendous amount of energy generation, right, we have all this gravitational pressure because now the star is more condensed. And we have all of this extra heat, right, from all of these new thermonuclear reactions going on. We've got tons and tons of energy generation. And in about 100,000 years, the star burns helium steadily in the core with a hydrogen burning shell, right? So we've got hydrogen or helium burning here, and we've got hydrogen burning here. And at that point, because now we've no longer got this degenerate matter issue in the core of our star, believe it or not, the star actually kind of shrinks down to a more normal size. It's not drawn to scale, of course, but it's smaller than what it was when it was a red giant. We call this a horizontal branch star. And the reason for that is that if you look at the region that this kind of star occupies on the HR diagram, it's a little horizontal strip. So a star like our sun will burn helium into carbon, probably a little leftward on this horizontal branch because it has metals and stuff in it. Stars that don't have as many metals be sort of more to the right. But a star like our sun will burn helium into carbon for probably about 100 million years, a tenth of a billion years, if you want to think of it that way. And so what's going to happen now is that we've got hydrogen burning into helium and helium burning into carbon. And so now we're going to end up with a carbon degenerate core. And it's going to stack up, you know, just like Legos being snapped together, right? It's going to be stacked as tightly as possible with tons and tons of electrons being bound to each atom in the lowest possible stacked up set of energy states that it can manage. And we're going to have the same problem again. As the carbon shrinks down and becomes degenerate, more matter from the body of the star is going to be pulled into the hydrogen burning core, and more matter is going to be pulled into the helium burning part of the core. And again, we're going to have a runaway energy generation effect. And guess what's going to happen then? You probably guessed it. The star is going to expand once again because, again, it can no longer compete with its gravity, right? The energy generation is so much greater than its own gravitational force that it's going to expand again and become this time what we call an asymptotic, ASYMPTOTIC, red giant. And this time, it's going to generate so much more energy than the star is going to be able to handle that eventually the outer layers of the star are just going to blow away. Now what's going to happen then is essentially, remember that a star is made up mostly of hydrogen gas, right? And so all of this matter is going to blow away and just become a giant gas cloud. We call that a planetary nebula. A star like our sun is probably going to lose about 40% of its mass into this planetary nebula. And what's going to get left behind, so remember we had hydrogen burning into helium, helium burning into carbon, and we had degenerate carbon. And so now we're going to have just a degenerate carbon core. We call this a white dwarf. And that is essentially the ultimate fate of a low-mass main sequence star like our sun. Now I'm going to give you a brief recap of this process, but first, there are a few images of some planetary nebulae in today's image bank. I think the 13th one? If you want to follow along, there are 4 of them. The first one, we call this the Cat's Eye Nebula. And it's probably pretty simple to see why. Now the book says some racist ass shit about the second one. The one that looks like kind of like a face with a nose on it. The book says, and we astronomers do not say this shit, okay? The book says something about it being called the Eskimo Nebula, and that's racist. We astronomers call that the clown face, and I'm pretty sure you can see why, right? There's this very visible kind of a red nose, like, you know, the red noses that clowns have when they honk, and it kind of looks like up at the top it has like the puffy clown hair. Yeah, I don't know where they got that, but we don't call it that. It's pretty gross. The next one, the one that kind of looks like a big pink cloud, try to guess what they call it. You can pause the video now if you feel like trying to figure it out. I think we call that the owl head or something. And you can kind of see it, right? There's 2 like sort of lighter circular kind of features that kind of look like, you know, like the feather patterns around an owl's eyes. The last one, I think they call it the dumbbell or the barbell, and I never really kind of saw that one. It always kind of looked like a donut or something to me. I don't know. But in any case, those are the planetary nebulae that get left behind when we eventually end up with just this hot electron degenerate carbon core that we call a white dwarf. So, let's sort of recap the process here. We start off with a huge ball of gas and dust and stuff, right? Mostly hydrogen and about 25% helium. And then over the course of time, you know, it may be spurred on by, you know, a passing star or a supernova or something like that. And that causes, you know, a bunch of material kind of all to move together, and eventually you have mutual gravitation from free fall contraction. That makes, you know, if it's a very, very large cloud, you know, you'll have several of these, but eventually you'll have a bunch of gas that kind of compresses down and spins out into making an accretion disk with a protostar at the middle, right? This protostar is actually very large compared to an actual star, right? And so it's much larger but also cooler than when the star finally compresses itself down under its own gravity such that there's enough pressure and temperature in its core that it can start its own thermonuclear reactions. And at that point, it becomes a true blue, bona fide main sequence star, like our sun. And of course, stars on the main sequence, where they spend about 90% of their life, burn hydrogen into helium. As they burn hydrogen into helium, the helium deposits itself sort of as ash in the core of the star. That takes a long time, of course, but over the course of billions of years, maybe millions, if you're talking about a really, really super hot star like a blue class or an class O star, like a really hot blue star, and then longer, of course, if you're talking about a very dim, very comparatively cool red star, and then about 10 billion years or so for a star like our sun. Up to 55, 56 or something like that for a class M star, and then maybe 10 million years for a class O star. But over the course of time, while the star's on the main sequence, it's going to build up helium ash in its core, and that helium, because there is not sufficient temperature and pressure, in order for that helium to fuse together to make carbon, it's going to crunch down and become degenerate due to the tremendous amount of gravitational pressure inside the core of this star, right? Until eventually, it compresses and compresses and compresses, and so much of it builds up that it shrinks down, becomes degenerate, and the rest of the star has to move inward to compensate for the loss of volume. That causes a large hydrogen burning shell sort of on the outside of the core, and that causes a runaway energy generation effect, which causes the star to blow up and become a red giant. And eventually, it gets so hot, there's so much hydrogen burning, that eventually the pressure and temperature is sufficient for a a helium reaction to occur, right? We call it the triple alpha process, where you have two heliums make a beryllium, and the third one joins the party to make it a stable carbon. And as a result, all of the helium catches fire, an event we called the helium flash. That causes all of the helium in the core of the star to burst outward and become non-degenerate once again. And that causes the star to shrink, the outer layers of the star to shrink, and become what we call a horizontal branch star. But now we've got hydrogen and helium burning, and that's going to cause a crazy runaway energy generation effect, the likes of which the star has never seen. And so it's going to blow up and become a red giant the second time. We call it an asymptotic red giant, right, or an asymptotic giant star. And eventually, now we've got hydrogen burning into helium and helium burning into carbon. The carbon is going to deposit in the core of the star, become degenerate, and that's going to cause more matter to move into the nuclear reaction zone, the core of the star, causing even more energy to be generated until eventually it's going to blow away its outer layers in a planetary nebula ejection event, leaving behind just the degenerate carbon core, the white dwarf. Now, white dwarfs, they're going to stick around probably quite a long time. They're going to be not the last objects in the universe, but they're going to be among the last remaining objects in the universe after the last star burns out. They do give off energy, so they will eventually fizzle out as well. But it's going to be a very, very long time before that happens. Now, there is a series of images, starting with the image titled at the top, Zero Age Main Sequence. And what we mean by zero age main sequence is, if you imagine a cluster of stars, let's say there was a huge nebula, molecular cloud, whatever you want to call it, right? There was a huge cloud of gas, and it made thousands, maybe millions of stars, kind of all together, right? And they all turned on, so to speak. They all became stars around the same time. What kind of distribution would you expect to see? Well, you would expect to see some really hot blue stars, some really dim red stars, some stars in between. Essentially, the entire main sequence, right? That's what we call a zero-age main sequence. And if you have a population of stars, like in what we'll see later, a cluster, right? There's globular clusters, there's open clusters. If you manage to find a cluster of stars that has sort of the same age population, you would expect to see kind of all of them, right? Now, as this population gets older, right, as time passes, millions, tens of millions, hundreds of millions, billions of years, and so on, eventually, what's going to happen to that zero-age main sequence distribution? Well, remember, the class O stars, the stars that are kind of up at the top left, the farther to the left, of course, is a higher surface temperature, right? The hotter stars are going to burn brighter. They're going to release more energy. They're going to burn through their fuel more quickly, right? And we can see that they're farther up on the vertical axis of the HR diagram in that they're much brighter, right? And that gives us a clue as to how much energy they're generating. So the really hot blue stars are going to burn through their fuel much more quickly. And as a cluster of stars, a population, a zero-age main sequence population ages, we would expect to see those stars are going to evolve off of the main sequence first, the really massive ones, right? And the older the population of stars is, the further down the main sequence that turn-off feature is going to be. If a cluster is about 10 billion years old, then we would expect to see a turn-off that's somewhere near our sun's location on the HR diagram, right? Our sun is supposed to live about 10 billion years. And as a matter of fact, we took a picture of, or it's not a picture, I guess a snapshot, right? We collected a bunch of data on a cluster of stars, and we saw exactly what we would expect to see. We saw the turn-off feature, we saw this red giant branch where stars are evolving off of the main sequence, and we even saw the horizontal branch where stars that are starting to burn helium should be located on the main sequence. And so again, what we had to do to make sure that our understanding is correct, we propose a model based on our physics, right, on our understanding of particle physics and nuclear physics and so on. And we proposed a model of what should happen, and we looked for analogs of it out in the universe, and we found them. So we know we're on the right track. And as a matter of fact, we've been able to piece together main sequence distributions for tons of different star clusters. And so we think that we've got a pretty good handle on how it is that stars evolve off of the main sequence. Anyway, this entire track where we start with a low mass main sequence star and we end up with 2 times a red giant and then eventually we end up with a white dwarf, that only works for low mass main sequence stars, things that are maybe a little more massive than our sun all the way down to tiny little class M stars. Right? For more massive stars, different things will happen. But we'll talk about that next time. Let's talk a little bit about the ultimate fate of white dwarfs. Remember that most star systems are not single star systems. Most star systems are binary or sometimes trinary or what we call ternary star systems, right? Multiple, usually 2 sometimes 3, and as a matter of fact, sometimes um, the fate of one star in a binary star system can have effect on the fate of its partner. Now, if one star blows up, becomes a red giant, eventually blows away all of its material, and leaves behind a white dwarf, if all of that material, as this star blows up and becomes a red giant, right? If that material crosses over its Roche limit to its partner, you guys remember the Roche lobes, right? Also, we sometimes call the Roche lobe, we call that a Hill sphere, right? If the star blows up and becomes a red giant, then if that material expands enough that it spills over the Hill sphere, over the Roche lobe, over the Roche limit, whatever you want to call it, if it spills over, the other star, its companion star, can collect its material, right? And so if a star blows up and becomes a red giant, its companion star can pull in a bunch of its material. Now, if a star blows up and becomes a red giant, right, and all of its material gets blown off to its partner, and it leaves behind a white dwarf, funny things can happen, right? If a white dwarf gets left behind and its partner gives it a bunch of material, so let's just kind of draw this out. There's a series of images in today's image bank. But let's say, we got a star here, we got a star here, and this one blows up and becomes a red giant, right? And we've got, let's say this is our Roche limit here, and this is our Roche limit here. And if this one blows up enough that it crosses over, all of this material is going to go over to this star, right? So what's going to happen then? Well, if this leaves behind a white dwarf, this star is going to get bigger, right, and hotter. Eventually, it's going to evolve off the main sequence too. And it's going to blow up at some point and also become a red giant, right? And when it passes the material back, white dwarves kind of have a funny, peculiar sort of possible fate. There's a mass limit for white dwarfs. If a white dwarf gains mass such that it goes over 1.4 solar masses, it blows up, it explodes, it completely disintegrates in a very bright, incredibly brilliant event. This is called a type 1, it's actually a lowercase a, I almost wrote it as an uppercase, 1a supernova. This is one of the brightest events in the universe. It's so bright that we can see it basically all the way out to the edge of the visible universe. It's incredibly bright. So much so that it completely destroys the star. There will be nothing left, right? All of the particles just kind of get disintegrated. They fly every which way out into the universe. Now the important part, because they all happen at exactly the same mass limit, they all have exactly the same brightness. Brief preview of coming attractions. Because they all have exactly the same brightness, we know how bright they are supposed to be. And if we can compare that to how bright they appear, what can we figure out? We can determine how far this supernova event is from us. That makes it what we call a standard candle. Anyway, that'll become important in the coming weeks. I hope you have enjoyed today's lecture as much as I have enjoyed giving it. Get a hold of me through the normal channels, of course, if you have any questions, and we'll see you next time.